Okay, section 6.4 is work. Um, Again, I think I made a mistake on the papers that you guys got, which probably has a 6.3 on it, or a 5.4, excuse me. Um, don't worry about that. It is 6.4 in the new book. So what we're going to do is we're going to calculate the work done on an object, and anybody that's taken physics knows that this is actually a very applicable thing to physics. Um, and we'll talk about the homework at the end. This one is really short. Going to try and keep this video under 20 minutes. Let's see how we do. So most of us think of work as the total amount of effort required to complete a task. How much work do you have to do? Well, it's how much effort do I have to give to complete a task. Mathematically, it's actually a similar concept, but it's going to require the concept of force. The idea of force can be thought of as a push or a pull of an object in a specific direction. So again, if you've taken physics, this is really probably coming back to you. Most commonly, we're going to think of force in terms of Newton's second law, which states that force equals mass times acceleration. Most of us have definitely heard of that one. Well, if we put this into terms of calculus, since we know that the acceleration is the second derivative of position, we can call force mass times d squared s over dt squared, or the second derivative of position, where s is the position function. And if acceleration is constant, we get the most common formula that we're going to use for work, which is work equals force times distance. Because if the acceleration is constant, it's going to give us the distance. So work would equal force times distance. Important units here. If F is measured in newtons and distance is measured in meters, the unit for that, if you multiply the distance in newtons times meters, is actually what's called a Newton meter, more commonly known as a joule. If F happens to be measured in pounds, which is the US customary system, and D is measured in feet, then W is actually what's called a foot-pound, and a foot-pound corresponds to approximately 1.36 joules. All right, that's important as far as knowing the conversions back and forth. Okay, so example 1, how much work is done lifting a 1.2 kilogram book off the floor to put it on a desk that is 0.7 meters high. So we're going to use the fact that acceleration due to gravity is 9.8 meters per second squared. And then we want to know how much work is done in lifting a 20-pound book, a 20-pound weight 6 feet off the ground. So in letter A, we need the force. To know the work, we need the force. And the force is the mass times the gravity. Because what we need to do is we need to figure out the force that you would actually have to lift something off the ground, because if you think about it, as you lift something off of the ground, what gives it weight is the fact that gravity is pulling down on it. So this, the gravity part, is to counter the gravity exerted. Okay, so the force is going to be, let's see, the mass of this book is 1.2 kilograms. And gravity, it told us to use 9.8. So if we multiply those two things together, our force that we have to exert is 11.76 newtons. That's the force that's going to be required. Now, in order to find the actual work done, the work is the force times the distance. And the distance that it says is 0.7 meters high. So it looks like my work is going to be 11.76 times 0.7 meters, which is going to give us a work of 8.2 joules. Okay, not really any calculus needed there. This is just standard physics stuff, just to get you familiar with the concept of work. And part B, how much work is done in lifting a 20-pound weight 6 feet off the ground? So the work in letter B is going to simply be the force, which is 20, times the 6 feet off the ground. So we really get 120 foot-pounds. And you might ask yourself, well, wait a minute, why didn't you do anything with gravity? The reason I didn't do anything with gravity is because it's not necessary to multiply by gravity when we're given weight in pounds. The pound actually takes care of the fact that the gravity is already exerted in there. So if you're given it in pounds, you don't need to use the gravity. If you're given it in kilograms, then we're going to have to use the gravity. All right. So all that works fine if the force is constant. What happens if the force is variable? If we think of force as being constant on a very small interval, so you can have a constant force for a really tiny small amount of time, and then as you're pulling, another really small amount of time, and then another small amount of time, and then another small amount of time until you actually get the whole thing done. That's the idea. As the interval of time gets smaller over a given bigger interval, we can then get back to the concept of an integral. So if we let the given small intervals approach infinity, small time intervals approach infinity, then we can use a definite integral to find the work done given a force function. So the work done would simply be the integral of whatever the force function is, f of x dx. All right, let's take a look at one example there. All right, when a particle is located a distance of x feet away from the origin, a force of x squared plus 2x pounds acts on it. How much work is done in moving it from x equals 1 to x equals 3? All right, again, the fact that this is in pounds means we can ignore the fact that there's any kind of gravity. It's already taken care of in the pounds. So work is going to be the integral. Let's see, we're going from x equals 1 to x equals 3. So how much work am I going to have to be done over that interval? And my function, which is going to be creating the force, is x squared plus 2x. Okay, this should be relatively simple. This was your force, the dx is your distance. So let's integrate 1/3 x cubed plus x squared from 1 to 3. Plugging in a 3, let's see, 3 cubed is 27, 27 over 3 is 9, plus 3 squared is 9.
Good evening, parents. We are very...
Plugging in 1, we get 1/3 plus 1. Okay, let's see, we got 9 plus 9 is 18, minus 1 is 17. So we get 17 minus 1/3, putting everything into terms of thirds. 17 is 51 thirds minus 1/3. So we should end up with 50 thirds. That is the amount of work done on that particle to move it from 1 to x equals 1 to x equals 3 if x squared plus 2x pounds are acting on it. Okay, so these were relatively easy. There are a lot more work problems that are actually much more challenging to do. And in Calc 1, There's a lot more that goes into it in Calc AB and Calc BC, but we don't actually teach this in Calc AB BC. It's not a tested topic, so really it's kind of a Calc 1 topic or maybe a Calc 2 topic depending on what your school of choice would be. In either case, there are some much more complicated types of problems that are way easier to do using Calc 3 methods, and we're going to get into those a little bit later in the course. So because I didn't want to get too heavy into the work stuff, there's no homework associated with this in particular section. So the only homework that you have to do is going to be from the cylindrical shells. All right, that should be good enough.